This is part 5 of the Module 10 lecture. In this part, we're going to talk about an example of how to perform a test of independence. In this example, we have a study that 2,700 Rhode Island residents were classified according to income and time elapsed since they last consulted a physician. The question is whether this data provides sufficient evidence to indicate that there is an association between income and time since the last visit to a physician. And the test is to be done at a significance level of 0.005. All right, in this case, you can see that we have that level of income, and it's been broken in the following classes: less than 3,000, 3,000 to 4,999, 5,000 to 6,699, 7,000 to 9,999, and more than 10,000. And then here you have the last visit to the physician, which has been classified as within the previous 6 months, within 7 months to a year, and more than 1 year. And if you sum the rows, you see that they correspond to these values. And if you sum the row totals, you get the total amount. The same, if you sum all the entries across rows for each of the columns, you get these numbers and you see that they match this total. So this is a contingency table. All right, so in here, the problem is telling us if there is an association between income and the time since last visit to a physician. So we're dealing with a test of independence. All right. Again, we're going to follow the 5-step process to test a hypothesis. And so let's follow these 5 steps. All right. And the first step is we need to establish the hypothesis, indicate the direction of the test, and specify the significance level. So in this case, under the null hypothesis, you want to see if income and time since last doctor's visit are independent under the null hypothesis, and under the alternative hypothesis is the income and time since the last doctor's visits are dependent. This is a right-tailed test. It's the only direction that we have in this case, and the significance level is 0.05. In step 2, we need to determine what distribution to use. This is a 5 by 3 contingency table, and we need to calculate the expected values for each of the cells to determine if these are at least 5. If they are at least 5, and because the contingency table contains discrete classifications and discrete counts, then we will be able to use a chi-square distribution with 5 rows minus 1 times 3 columns minus 1, that is 8 degrees of freedom. All right, let's calculate the expected values. All right, to do the calculation of the expected values, we do it cell by cell. So for example, for cell 1, which is row 1, column 1, we take the row total for that row times the column total and divide that product by the total amount. So it's 259 times 1,640 divided by 2,764. That gives you this number. For the cell 1, 2, row 1, column 2, this one right here. So in here we are multiplying the row total, which is the same because we're still in row 1, 259, times that second column total, 467, divided by the total amount. So that's this calculation, that gives you 53.13. For the first row, third column, again, so we multiply 259 because we're on the first row, times the third column total, 557. We multiply these two numbers and divide by this, and we obtain this frequency. So, and then you continue with the second row, and then you multiply the second row total, 326 times 1,640 divided by 2,764, and you obtain 193.43. So the expected values in here have been calculated already, and they're shown within the parentheses. And in here, with these dots, I'm just saying that there is all these calculations, 4 by 3, 12 calculations, and we end up with the fifth row, third column, and as you can see, it's 1,197. That's the fifth row times the total of the third column for 157. We divide by 2,764, and that's how we obtain this 241.22. All right, so you can see that all the expected values are larger than 5. So then we're justified in using a chi-square distribution with 8 degrees of freedom. All right, again, these problems tend, depending on the size of the table, they could have a lot of calculations to do. All right, to calculate the test statistic, now we're going to use this table where we have the observed frequency and the expected frequency, and we're going to apply this formula. So again, we're going to start with the first row and then the first column, and then we go to the second row, next column, and so on. But you can see, if you don't understand these indices and the order, just look at what we're doing. So we're looking at the first row. We take the observed frequency minus the expected frequency. We square that and we divide it by the expected frequency. So that's the value for the first cell. For the second cell, we do, again, the observed frequency minus the expected frequency, square that and divide by the expected frequency. Then we go to the third column for the first row. So there we have 35 minus 52.19 square and divide that by 52.9 square. So this gives us the chi-square value for this cell. And then we go to the second row. So now we have 227 is the observed frequency minus 193.43, which is the expected frequency. We square that and divide by that expected frequency. Then we go to the next row. So we go 54 minus 66.87, square that and divide by 66.87. So that's for this second row, second column. Then the second row, third column, we do 45 minus 65.7 and divide by 65.7. And then you continue going row by row until you get to the very last calculation, which is the fifth row, third column, and you do 259 minus 241.22 and divide by 241.22. As you can see, 12 calculations like this, a lot of calculations. But at the end, you end up with the value of the test statistic, 47.9. All right, now that we have the value of the test statistic, then we can proceed to the next step, which is either follow the critical value approach or the p-value approach. If we follow the critical value approach, then we know this is a right tail test. So we are looking for the critical value on the right tail of a chi-square distribution with 8 degrees of freedom. To find that critical value, we look at the row of 8 degrees of freedom and look at the column at the top with the probability of 0.05. If you look at table 6, again, you will find that the critical value is 21.955. So the rejection region is for any chi-square value larger than 21.955. Now, for the p-value approach, again, you need to look at the row for 8 degrees of freedom and see where this the value of the test statistic is, 47.9. If you look at the values on that row, you find that 47.9 is larger than the last value of 21.995 for a probability of 0.05 in the row of 8 degrees of freedom, of course, in table 6. So this is telling us that the p-value is smaller than 0.05. If you want to find the exact p-value, then you can use this formula on Excel, and you find that this is 0.000001032. Very small, but that's the value. All right, now that we have found these quantities, we can go on and to make a decision about the null hypothesis. So you see that a calculated value of the test statistic is 47.9, which is larger than the critical value of 21.995. That's telling you that the test statistic, excuse me, is in the rejection region. And also the p-value we know is smaller than 0.05. So both criteria indicate that the null hypothesis should be rejected. So the level of income and the time since the last visit to the doctor are independent. Is rejected. Well, that's the assumption is rejected. So there is a dependency between income and the time since the last visit to a physician. So the interpretation of the decision then is at the significance level of 0.05, we conclude that the income of a patient is related to the time since his or her last visit to a physician. Now again, this is, you may feel that it doesn't tell you very much other than these two variables are related. So what you could do is then look at the chi-square values. I'm using these Excel graphs, and just to see where the larger discrepancies are. And also in here, then you see that in this one we're looking at the difference. Well, let me see. This is the chi-square values, and this is the difference of the observed minus expected values. And of course, if there is a match, then all these cells should be very close to zero, like in this case for this level of income. But you can see, for example, for low incomes, people tend to visit the doctor more frequently. In other words, in the first 6 months, more than expected. Whereas people for very high income, the frequency of visiting doctors is less than what is expected for the 6-month period, but not for the 7-month to 1 year period. So again, I think the bigger discrepancy is right here, and the other ones are right here for the low income. Again, I'm just providing this to help you see how you could further analyze the data in this contingency table. Again, for our purpose, we will stop at this point. I will only ask you to interpret the decision from the hypothesis test. All right, this is one example of how to perform a test of independence. In the textbook, there's another example. So you can look at that and look at this and see the procedure. And again, the problem with this is that the bigger the contingency table, the more difficult the calculations and the better justification to use a software package. In fact, here is the typical output. If you were to perform a chi-square test of independence or homogeneity, the output will look like this. And of course, they only produce the p-value. They give you the chi-square value, the degrees of freedom, and then they show you the table, and they show you not only the observed value, they show you the expected value as well as the chi-square of each cell. All right, again, this course is not taught using software, but if we were using software, we will not do the calculations. We will use the software to produce this output, and then we'll just interpret the output. All right, I will stop here, and in the next recording, we'll look at an example of how to perform a test of homogeneity.